In this video, we're going to begin discussing Lagrange multipliers. These provide a tool for solving optimization problems where we have constraints on the variables. All right, so we already know how to find extrema of a function of two variables when we're on a given domain, such as on a triangle or a rectangle. But now we're going to really focus on what happens when we have a constraint on the variables, and we'll make clear what that means as we go through this section. So to get started, let's suppose that we want to either minimize or maximize, depends on obviously the problem. So we either want to maximize or minimize a function. So we want to maximize or minimize values of a function f(x,y) subject to a constraint which we're going to give by an equation. So our constraint we're going to call g of xy equals k. Right? So what we mean by this is that we want to only consider the points xy that are on the curve g of xy equal to k. Right? That's just a curve in the plane. We want to only consider the points on that curve and find the extreme values of the function f among those points. So before we know if we want the maximum or minimal value in a triangular region or some other region like that, we know how to do that using critical points. But if we want the maximum or minimum value on a curve, what we've learned previously will not apply. And so in this hypothetical context where we want to maximize or minimize these values subject to this constraint, what we're going to do is we're going to start by considering the level curves of the function f. And so we're going to draw a picture. So remember, we're working in the plane here. So I'm going to start by drawing my constraint. So my constraint is just some curve. It's g of xy equal to k. And, who knows what it looks like. Maybe it looks something like this. All right, so I'm just going to label this as g of xy equal to k. And then I'm going to draw my level curves of f. Now, the level curves of f, if you remember, what we do is we set the function f of xy equal to a constant k, and then draw that curve, and we do this for many k. So again, let's say we have level curves that look something like this. And again, this is just kind of an arbitrary function that I'm making up. So let's say this is the level curve we get by setting f of xy equal to 7. And this is the level curve we get by setting f of xy equal to 8. And let's say this is the level curve we get by setting f of xy equal to 9. And I'll draw one more. Here's f of xy equal to 10. So if this were our function, if these were the level curves of our function, and this was our constraint g, the plan is to find the largest the point on function g where the function value is largest. All right, so if we just kind of go through there and we look at the points on g, well, we know that this point and this point have a function value of 7 because they're on the level curve f of xy equals 7. And we know this point and this point have a function value of 8 because they're on the level curve equaling 8. And we know this point right here, I'm going to circle that in a different color, has a function value of 9 because it's on that level curve. And then there are no points. There are no points on the level curve of f of xy. And so what we see from this picture is that our point of interest is this point right here. This is the point that is going to maximize our function value with the constraint being on the curve g of xy equal to k. It's the largest function value of all those points. Right? And so what we see that's special about those about that particular point is that the two curves, the curve given by the constraint and the level curve, are actually tangent to each other. They just touch at that point and then back away. And of course, what that actually means is that they have the same exact tangent line. Right, so what we just did in that picture, right, we wanted to maximize f of xy with respect to the constraint g of xy equal to k. So what we want to do is we want to find the largest value of c such that f of xy equal to c, that level curve, this is what we drew in red, intersects the curve g of xy equal to k. Right, and that's what we did in the pictures. We had all these level curves. I think we had it for 7, 8, 9, and 10. And we saw that the level curve for 9 just touched that point on the curve g of xy equal to k at that one point. And any level curve further out, if we went any further out towards that level curve of 10, then those two curves would not intersect at all. And so as we observed in that graph, this appears to happen when the curves just touch each other. Right, where they just touch at that single point. And in other words, what that means is when they have a common tangent line. And this is something that we can work with, that we can try to determine and then be able to compute. Right? And so the way that we're going to approach this is by using the fact that if they have the same tangent line, the gradient vector for both the function f and the function g evaluated at that intersection point, these must both be orthogonal to that tangent line. In other words, they are parallel. So these are parallel vectors. That means they point in the same direction. And so the big punchline here is that the gradient vector of f is equal to some constant, which we're going to always call lambda. That's the standard symbol for Lagrange multipliers, which is what this is. The gradient of f is going to be some constant times gradient of g for some real number lambda. Right? This is what it means for two vectors to be parallel or to be in the same direction, is that they are scalar multiples of each other. Right? And this symbol lambda, as I just mentioned, is referred to as the Lagrange multiplier. Right, so the key to solving an optimization problem with the constraint is to solve this equation right here. Right? Now notice this equation is actually a vector equation. Both sides of the equation are vectors. And so if we're in the context that we're working here, this is actually two different equations. It's actually an equation that the partial of f with respect to x is equal to lambda times the partial of g with respect to x. That's the first component of our vectors being equal. And the second equation is that the y component, the partial derivatives with respect to y of f and g, are also related with the same scalar lambda. So we actually get two equations involving functions, involving numbers here. And so often we'll have to solve a system of equations in order to use this in a problem. So let's look at an example. Let's say we wanted to find the global extrema of the function f of xy equals x squared plus 2y squared, subject to being on the constraint on the circle x squared plus y squared equals 1. All right, so a couple quick things about this problem before we go through and solve it. The first is we want to consider only points on the circle, not points inside the circle. So this is a circle, not a disk. If we wanted to do a disk, we would want to go through and use critical points and things like this that are inside the disk. But in this case, we only want the points on the disk. And the second thing is we know f of xy, we're given our function, but our constraint function here, g of xy, is going to be the function x squared plus y squared. We do not have to consider the 1 as part of that because we're solving this with respect to the constraint g of xy equals some number k. And so that 1 over there really doesn't make a difference. We'll see where it comes into play, but at least in terms of coming up with g, that's not a vital part. That constant can be whatever we want it to be over there. So if we approach this like we just talked about, we want to compute the gradients of f and g. Right, so the gradient vector is just the partial with respect to x and y. So differentiating f with respect to x yields 2x, and with respect to y yields 4y. And the gradient of g of xy, so we just labeled g of xy here as x squared plus y squared. The partial with respect to x is 2x. The partial with respect to y is 2y. Okay. And so we want to solve the equation gradient of f equals lambda times the gradient of g. Okay. And so if we can split this up into a set of 3 equations. If we compare the first component, we see that 2x is going to equal lambda times 2x. This is from our setting the first components of our vector equation equal to each other. The second component is going to yield 4y equals lambda times 2y. All right, so these are the 2 equations we get from our vector equation, but then we also will need the constraint equation, x squared plus y squared equals 1. Right? Because we only want to consider those points x, y that are on the curve. And so the solution to our problem will be a solution of this system of equations. And so once we get this system set up, Lagrange multipliers gives us a great way of setting up this system. At this point, it's an algebra problem, and we have to look at the particular system that we get, what equations, forms we have, and how we can use them together. And so we're going to look at, in our examples, we'll look at a couple different approaches you can take to how to solve this. But this is really the hard part for solving Lagrange multipliers problems, is that we have to use the equations that we're given, and depending on what types of equations we have, gives us different techniques for solving that system. All right, so on the next slide, we're going to solve this system, but just to make it a little bit easier to follow, I'm going to number these equations 1, 2, and 3. And so on the next slide, if I just refer to equation 1, I'm referring to the equation 2x equals lambda 2x. If I'm referring to equation 2, I mean 4y equals lambda 2y. And I'm just going to follow this convention just to make our work a little bit easier and it's more straightforward to follow. Right, so for this particular system, I'm going to start with equation 1, which was that 2x equals lambda 2x. And from equation 1, I know one of 2 possibilities are going to happen. It's possible that x is equal to 0. And if that's the case, then both sides of that equation are equal to 0. And if x is non-zero, we can divide both sides by 2x, and we get lambda equals 1. Right? So from equation 1, we get that either x has to be 0 or lambda has to be 1. Now, it's most people would probably get the lambda equals 1, but it is important that we consider the fact that x is possibly 0 is also a solution to that equation. So we want to make sure when we solve this, we're looking for all the different ways a potential one of the equations could be true. Right? So we know we're down to one of these two things, so we can just look at each of these two cases. Right? So let's say that x is equal to 0. Right? So if x is equal to 0, then we can go down to equation 3. I mean, equation 2 doesn't involve x at all, so saying x is equal to 0 is not really beneficial to anything. So if I have x equals 0, we consider equation 3, and I let x to be 0 there, and I get y squared equals 1. All right, 0 squared plus y squared is equal to 1. And I know we have two solutions to that equation, so y is either plus or minus 1 in that context. Right? So if x is 0, I know y has to be plus or minus 1. Right? Well, let's also look at what happens when lambda is equal to 1. Right? If lambda is equal to 1, I'm going to turn my attention to equation 2. And if I turn my attention to equation 2 and lambda is equal to 1, we get the equation 4y equals 2y. Okay? And the only way this is possible is if y is equal to 0. And we can divide both sides by 2, or you can subtract 2y from both sides, however you want to get it done, and you end up with y equaling 0. Right? Now, if y is equal to 0, now we can go down to equation 3. Assuming y is equal to 0, I get x squared equals 1. And thus, x is plus or minus 1. Right? And so we've just found a variety of potential points. Right? We know x is 0 or lambda is 1, and in each of those two cases, we found the values of x and y. So in this case, what we can do is we just check our possible extreme values. So our possibilities are, in our first case, we had x equals 0 and y plus or minus 1. So 0, 1, and 0, negative 1. In the second case, where lambda was 1, we ended up getting x being plus or minus 1 and y being 0. And that's it. So we have four possible values for our extreme value of our function. And so one of these will be the global max, and one of these will be the global min. And so in order to determine which is which, we're just going to check each of these by substituting the x and y coordinates into our function f. Right? And when we do that, we see that f of 0, 1 is going to equal 2. We see f of 0, negative 1 is going to equal 2. We have f of 1, 0, which is going to equal 1. And f of negative 1, 0 is also going to equal 1. And so if we consider all the points on that circle, the global max actually occurs at two different places. It occurs at 0, 1 and at 0, negative 1, so at the very top and at the very bottom of the circle. And our global min occurs also at two places, at 1, 0 and negative 1, 0, so on the very right and very left points of the circle. Right? So notice that another thing that we learned from this is that if we take any point on our circle and evaluate it at our function, we're going to get a value between 1 and 2. And except for these four endpoints, we're not going to get 1 or 2. So we're going to be strictly between 1 and 2 at all other points of this circle.